So we're in Unit 7, the mole. We're talking about something new now. Remember, we were talking about how a mole is a specific quantity, and now we're talking about ways that we can actually use this specific quantity. So the first thing, or the second rather, we did percent composition. We can make a molecular formula. We can figure it out. We can determine a chemical formula of a compound just based on lab data. So the molecular formula shows us the actual number of atoms in a compound. We're going to see two types of formulas here. This one shows us exactly how many of each atom of each element are there. For example, if we look at glucose. Glucose is one that you came across in your biology class. It has a specific chemical formula, C6H12O6. And just looking at this molecular formula, we see that there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Looking at another, formaldehyde. It's a chemical, it's used in the industrial production of some chemicals, and it's also been used to preserve tissue samples in the past. Formaldehyde has a molecular formula. It is CH2O. Each molecule of formaldehyde has 1 carbon atom, 2 hydrogens, and 1 oxygen atom. So the molecular formula tells us the exact number of atoms. But there's another type of chemical formula that we'll come across, and it is the empirical formula. The empirical formula shows us the lowest whole number ratio. Somewhat like an ionic compound, it was the lowest whole number ratio. Same thing with a molecule. The empirical formula shows us the lowest ratio. But it does not always tell us the actual number of atoms. So let's look back at glucose and formaldehyde. In the glucose molecule, let's write this down again. You could reduce this number, you could reduce this number by dividing the number of atoms by 6. You can take a 6 out of the carbon, 6 out of the hydrogen, 6 out of the oxygen. This would tell us the lowest whole number ratio of the elements. So if you did that, we would get the empirical formula. The empirical formula of glucose is CH2O. It's reduced. Write that here. So you'll notice that the molecular and empirical formulas are not the same. If we look at formaldehyde, that was CH2O, it's already in the lowest whole number ratio. It cannot be reduced. And so we find that the empirical formula and the molecular formula of formaldehyde are the same, and it's CH2O. It's important to note that glucose and formaldehyde have very different properties, 2 completely different things. Glucose is a sugar. It's required in your body. Your body can't live without it. On the other hand, there's formaldehyde. Formaldehyde is toxic. At this point, you're probably wondering, what's the point of the empirical formula if it's going to change the formula and possibly confuse something required for life versus something that will possibly kill you? So two compounds that have the same empirical formula generally have different properties. Here's the difference between them. Empirical formulas can be determined easily from lab data. Molecular formulas require more information. We can figure out the empirical formula if we know the percent composition of the compound. So to find the empirical formula of a compound, we've got some steps here. Step 1, convert the percent to grams. For example, if you have 50%, we just make it 50 grams. It makes it easy to work with. Then you'll convert the grams to moles, divide by the lowest number of moles, and then simplify the ratio. So let's look at a couple examples. It's really easier to see how it works than to read about it. So in this first example, we're going to look at something that has 3 elements involved. It has potassium, it has manganese, and it has oxygen. You could just Google it and find a chemical formula, but there are 3 or 4 different ways that you could put these 3 elements together. And so you wouldn't necessarily know what we're talking about without doing the work here. This particular compound is 24.7% by mass potassium. It is 34.8% manganese, and it is 40.5% oxygen. So here's what we do. Step 1 says convert the percent of each element to grams. So what I'm going to do here is take this 24.7%, and I'm just going to say that we have 24.7 grams. And here's how we can do this. This is a side note. So we don't know the sample size. It's a question mark. So we don't know how much mass is actually there. All we know is a ratio. So what we do is say something we don't know, and we're going to say it's 100 grams. And that's how we get to here. And so it's an easy jump just to change that percent sign to grams. It's a ratio anyway. It's not really going to cause us problems. So let's go ahead and change manganese, 34.8 grams, and oxygen, 40.5 grams. Step 2 says convert the grams of each element to moles. And so I'm going to change this number to moles. And it's a quick dimensional analysis problem. And we're going to use the molar mass. Use the molar mass. And so for potassium, the molar mass comes straight from the periodic table, and it rounds to 39.1 grams. And that's the mass in 1 mole of potassium. So we'll go ahead and put this into the calculator, and it is 0.632 moles We'll do the same thing with manganese. Manganese on the periodic table, 54.9 grams. And putting it in the calculator says 0.634 moles. For the oxygen, you might be at a point where you don't even have to look this up. 16.0 grams per mole. And we find it is 2.53 moles. So the next step says divide the moles of each element by the element with the lowest number of moles. And so if you look at these three numbers, we're picking the smallest one, and that would be this one. This one's the smallest, it's the lowest number of moles. And so we're going to divide everything by that number. Divide by 0.632 moles. Divide by 0.632 moles. So for the first one, dividing by itself, we don't have to put that in the calculator, it's just a 1. The next one, 0.634 divided by 0.632. This comes out to be 1.003 and then some other things. We're going to round this off. So what we're doing here is looking for the numbers in the chemical formula. And so I'm going to say this is really close to 1. In fact, due to our rounding back here, it probably would have been 1. Then we have 0.253 divided by 0.632. 0.53 divided by 0.632. And with this one, we get 4.003 and then some numbers. But just like the previous one, this is telling us how many oxygen atoms are in the formula. So it's approximately 4. These are the subscripts in the chemical formula, in the empirical formula. And so let's write this here. Subscripts in empirical formula. This one, this one, this one. And so what we end up with is an empirical formula that looks like this. K, and there's only one of them, so we just leave it off. Mn, and it's a 1, so we just leave it off. O4. So this is the empirical formula of this particular compound. It is potassium permanganate. Now, a lot of times the question comes up, how do I know what order to put these in? And that can be a challenge. And in general, I try to make it so it's not too big of an issue. But I would typically just go in the order that I was given the elements. There are some more specific rules, but we'll leave those for another day. All right, we have some room for a little more, or we should. I'm going to do one more. And this is something that we'll work with together in class just to make sure that we all understand. So here we have a compound that is sodium 43.4%. And it is some carbon 11.3%. Spread this out a little bit. And then we have oxygen, and the oxygen accounts for 45.3%. And we follow these same steps. So the first step says convert the percentage of each element to grams. And so all I'm going to do is say 43.4% is now 43.4 grams. Carbon 11.3% is now 11.3 grams. And oxygen 45.3% becomes 45.3 grams. Step 2, we want to change these numbers into moles. The reason we do this is because grams of sodium is different than grams of carbon because they have different masses. And so they don't quite compare right. But when we use moles, it takes mass out of the equation. Moles is a unit that can relate everything. So for sodium, the molar mass is 23.0, and that's the number of grams in 1 mole. Let's go ahead and put that in the calculator. And we find 1.89 moles. We'll do the same with carbon, and there are 12.0 grams in 1 mole. And this is 0.942 moles. And the oxygen molar mass is 16.0 grams in 1 mole. And this is 2.83 moles. Again, this comes back to the whole, we can't compare masses, but we can compare moles. If you look at this, oxygen and sodium account for about the same percent by mass, and they account for about the same number of grams. But when we put it into moles, they're different. We find that we actually have quite a bit more oxygen than sodium, and the reason is oxygen has a smaller molar mass than sodium does. Next step says divide the moles of each element by the one with the fewest number of moles, or the lowest number of moles. And that would be this one, 0.942. So we're going to divide this by 0.942 moles. We're going to divide this one by 0.942 moles. And we're going to divide this one by 0.942 moles. So we know that this is 1. And 1.89 divided by 0.942 is 2.0064. So it's approximately it's close enough. As long as you're within probably 1/100th it's going to not be an issue. 2.83 divided by 0.942. And this is 3.0042. It's approximately 3. And so these are my subscripts. And so I'm going to write the empirical formula. And so I'm going to start with the elements in the order that I was given them. Sodium, and this tells me that there are 2 of them. Carbon, and this tells me that there's 1 of them, and so I'm going to leave that subscript off. And then oxygen, and this tells me 3 oxygens. And so the empirical formula of this compound is Na2CO3, which is sodium carbonate.